Okay, so last time we discussed about homotopy groups and some sample computations of homotopy groups via the Van Kampen theorem. And you guys noticed how difficult it was to compute the the homotopy groups of even just the simplest classical surfaces such as the torus and the sphere. So it was hard to compute the homotopy groups. So I mentioned this already, but there's a downside between computing homotopies or homotopy groups and homology groups. So one is easier to compute than the other. Um, but the thing is, the other one that isn't so easy to compute gives a much richer theory or much richer detail to the space that we're studying. So in this lecture, we're gonna start getting into homology groups, and these are the ones that are more in depth when it comes to computation. So there's a lot of theorems, lemmas, and things that are steps that we can use to compute a given homology group of a certain space. So it's actually really nice to start with homology, but we wanted to give like a sort of intro as well to homotopy, just to give you guys a sort of sense of the scale of the entire course or the sense of the scale of the entire theory. So, what is homology? In a very loose sense, it's a much uh, looser form of a homotopy. So, uh, so if pi n of x a given space is our homotopy group, so n equals 1, no, I'm gonna use k. N equals 1 or k equals 1 is our fundamental group. Hk of x is our homology groups. So I'm not just saying one, I'm not just saying homology group, I'm saying groups because k is it ranges over the naturals. So it's a natural number from 0 up to some indeterminate point, or it's really defined up to the dimension of x. So when we go beyond the dimension of x, the homotopy or the homology groups vanish. So k greater than the dimension of x, and the hk of x is immediately 0. So that's one key fact about homologies. So there are many different types of homologies out there. There is the cellular homology, which works best with graphs or discrete Femboy spaces if we're gonna study them. There's singular homology. And there's another one, it's a subset of cellular topology which uses delta complexes. So we impose a delta complex structure on our space, or we induce a triangulation. And when we do a triangulation, it can either give us a delta complex structure or a CW complex structure. So it's a complex composed of a bunch of CW stuff. Or it can give us, or a triangulation would involve a bunch of simplices. So one of those three. Now the easiest, undoubtedly, among all of these triangulation or methods of triangulation, which gives us the homology, would be the delta complex. Because let's say we're trying to find the homology group of a torus. Well, breaking it down into its identification space. So it looks like this. Breaking it down into its identification space allows us to sort of compute the homologies easier. Because if we're going to do a triangulation with simplices, we'd have to sort of make this a bunch of tiny triangles. The entire space, actually. And then, I have to fill that up with a bunch more triangles. And we're going to find homologies from those triangles. And that's a very tedious process. But with a delta complex structure, we only have to concern ourselves with this type of object. So just two simplices, which is actually one simplices, or one simplex in total. Three, so I'm going to highlight them. So these are the same edge, or these are the same faces of a simplex, or a two simplex. So 1, 2, 3 edges, which is the same as this and this. And then simply just one. It's just one vertex, right? So it's much easier to do that. But yeah, if we do it via simplexes, we'd have to actually triangulate the entire thing, and it's although it would give us a much more accurate homology of the torus, it's very computationally intense. Okay, so before we get into homology, we need to first define a couple of concepts. And recall that when we're trying to find holes in our space, in our femboy spaces, what we're trying to do is embed a sphere, an n sphere, into the space, and then using that and using its homotopies to detect holes in the space. And then that's how we differentiate one space from another. So what we're doing, if I denote an n simplex, so I haven't defined what an n simplex is yet. So it's a pair of points, ti, t1 up to tn in Rn, such that the sums, they're linear combinations, is 1. So, of course, you can envision a 1 simplex as just a simple line. A 2 simplex is a triangle with the insides filled in. And a 3 simplex is a tetrahedron. Can draw the lines for shit. Okay. And then, of course, the insides filled in. So it's a volume now. And of course, a 0 simplex is just a dot. So 0, 1, 2, and 3. So the goal of the first step in homology is to embed the suitable or the appropriate simplex and simplex into your space, and then use that as a starting point to computer homology. It's like trying to find the area under a graph, wherein you're trying to fit it with a bunch of rectangles and finding the areas of those rectangles to find its homology. We cannot find the homology of a space on its own. We have to put something onto the space or embed something onto the space in order for us to find its homology. And that starts with the simplex. All right. So you notice back in the diagram of a torus, I'm going to draw it again so it's much cleaner, and I'll use different colors for the identification of each edge. So you notice that here, we only have one edge, one vertex, and then we have 3 edges. So, all right. So you notice that over here we have really just a bunch of 1 simplexes, but really it's a surface in the sense where if I do fold it up and then identify the requisite edges, it would give me a 2-dimensional surface. So the identification space of a torus is already a 2-dimensional surface. So there will be 2 simplices. There will be 2 simplices inside it, and 1 simplices and 0 simplices. So once we identify the 1 simplices, the 2 simplices, or the 3 simplices inside the space, what we want to do next is find a way to associate it with a given algebraic structure. So this is called the coefficient group. So G, we call it G. the coefficient group. So the coefficient group is something that we put into a complex called a chain complex, and from there we compute the homology group. So it depends on how many of each of these are inside your space, what given coefficient groups you have. So we have multiple coefficient groups. So let's define what a chain complex is. So definition, a chain complex is a sequence of abelian groups and I'll call them C0, C1, C2, on and on, such that, so I have a sequence. This sequence is, so it's from infinity down to C2, C1, C0, and then 0 itself is exact. Okay, and I have requisite maps, del 3, del 2, del 1, del 0, and don't confuse these maps, don't confuse those maps as the partial derivative. These are called boundary maps. And they map one abelian group onto the other. So those are boundary maps. And it's always the case that del 0 is 0. So the image of del 0 is always 0. And you guys will see why I stated that in a moment. Okay. So C2 over here is the abelian group associated with our edges. No, our two simplices that we embed in the space. So if there are two simplices there, then C2 is not trivial. All right, so it's not 0, it's not a 0 group. It must be some G. It's a G, a coefficient group. Or it's some direct sum of G. All right. It breaks down into one of those cases. It's either direct sum of our coefficient group, or it's just a single copy of our coefficient group. All right, so if I have three simplices in my space, then this would extend to a different sequence. So it's 0, C3, C2, and C1, C0, and then to 0. Del 0, del 1, del 2, del 3, and then del 4. And del 4 is 0, and so is del 0. Both these are 0 because what we're doing is just embedding the 0 group into C3, and really the only image it can take on is just itself inside C3. So when I'm saying abelian group, we're talking with respect to addition, because the identity element in each of these abelian groups are 0, and so when we're trying to find kernels, right, we need to set it equal to 0, not really 1. I think you guys can choose 1 as your identity, but I think it's much more computationally cleaner and easier if we just pick additive abelian groups. Okay. So depending on how many simplices you have, say you have a 4 simplex, then if you have a bunch of 4 simplexes or 1/4 simplex inside your space, then of course it would extend to a different sequence, C4. So each of these guys are associated with a given n simplex. So this C3 is associated with a 3 simplex inside your space, or a bunch of 3 simplexes inside your space. C2 corresponds to a bunch of 2 simplexes in your space. C1 corresponds to the edges in your space, or 1 simplexes, and C0 of course is your 0 simplexes, or your nodes, if we use the terminology of graph theory. So let's start simple and try to compute the homology group of a simple graph. So let's start with a graph with edges, with nodes. Okay, I'm gonna use a circle here. Node X and Y. And I have an edge A, and I'm going to orient it this way. What's the homology group of this graph? Okay, so let's lay down the definition of a homology group. So given the definition of a chain complex, the homology group, the kth homology group of X, is equal to the kernel of del k mod the image of del k plus 1. So if I want to find the zeroth homology group, I'm gonna first find the kernel of del 0. So every element in C0 that's sent to 0, which is practically just the entire thing, mod the image of del 1. So the map right behind it. So what precisely are the elements we get from putting elements inside del 1 from C1, right? So that's the homology group, the actual definition of homology group. All right, so let's first identify how many simplices we have in this graph or this space. So I'll call this, no, I'm going to use small x and small y. Okay, small x, small y, and then this entire thing is our x. So what's our first homology? So notice that right off the bat, we only have a 1 simplex and a 0 simplex. So C2, C3, all of those are trivial because we don't have any 2 simplices here. We don't have any 3 simplices here. If I embed simplexes and simplexes into here, we can only embed a 1 simplex and then 2 0 simplices. I'm gonna use a different color for that. So yeah, 1 simplex and then 1 simplex and 2 0 simplices. So once you identified how many of those are there, now you need to identify what are the coefficient groups associated with x, y, and a here. So what is G? Well, G corresponds to a free abelian group generated by each of these. So each type or each number of these guys. So x and y generate a single coefficient group or free abelian group that has 2 generators, which is x and y. And A generates a single, or corresponds at least, to a single homology group, or not homology group, I mean a single Cn or Ck, which is only generated by 1 element. So it corresponds to a free abelian group of 1 element. So A corresponds to a free abelian group just generated by itself, and then x and y, they generate a different abelian group that's spanned by 2 generators. So you guys can see right off the bat, this is isomorphic to to the integers, and this is isomorphic to the integers direct sum itself, or Z2. Though I don't think it's abelian. We assume it's abelian at this point because I mentioned in the last video that homology groups are like, the first homology group at least is the abelianization of the fundamental group or the first homotopy group. All right, so now that we identified our CNs, let's put them into our chain complex. So so Z and then Z2 and then off to 0. So there's our chain complex. So what are the way of visualizing this? Of course, our simplex here, if we translate it to our femboy theory, it's a bunch of fine femboys, right? So, with some leading femboys at the edges, which are the sort of the vertices of each of these simplexes. So we have 2 femboys right here, and then we have a fine line of femboys right here, and the fine line of femboys are represented by a singular femboy, alright? So it's A, and then, you know, if I femboyize this sequence here, it would be 0, of course, FZ, and then this is FZ direct sum, FZ, then 0. Alright, so, of course, each of these guys would be femboy structures, so you have to femboyize it first. But going back to the normal example, really the femboyization just carries on from when we actually compute the homology group. So it's best, if you want to compute the homology group for a given femboy space, what you want to do first is treat it as a normal space, a normal topological space, compute its homologies, and then once you compute the homologies, that's when you femboyize the structure. Alright, so how do we compute the homologies here? Alright, we need to find out what the boundary maps is. So this is del 0, del 1, del 2. Obviously, del 2, the image of del 2 is the same as the image of del 0, which is 0. So it's equal to the image of del 0, that's 0. So that's one thing right off the bat that we know. All right, so let's start with the 0th homology group. So H0 of X. So let's just go back to the definition and recall that it is the kernel of del 0 mod image of del 1. And this is where you want to recall your abstract algebra on how to do quotients, because we're trying to find a quotient group. All right. So let's start with del 0. So what is del 0? The kernel of del 0 is simply Z2, the entire thing that's sent. So everything in Z2 is sent to the 0 group, because notice how this is the only thing that we have here. If it's a Z1, that's a different story, right? Our kernel is it takes a bunch more steps to compute the kernel. But right now we know that the entire thing is sent to 0. So that's the kernel, Z2. All right, so what's the image of del 1? So when I have a bunch of edges and I have a bunch of vertices, recall that to associate them with a given free abelian group, what we have to do is subtract the terminal point and the initial point. So if I'm going from one way to another, this is why orientation is important in this case, because xy, supposedly it would be the same as yx, but right now we're picking an orientation so that it's much easier to compute, because if we want to consider both orientations, it's gonna be much longer. So it's the same thing anyway, because of course they're abelianization. So they're abelian, so it doesn't matter which way we go. So A, so the boundary of A, by the name of, that's why it's called the boundary map, because we're finding the boundary of a given simplex there. And what is the boundary of A? It's usually y minus x. Why y minus x? Because we're going from x to y, and it's always the procedure that if you're going from one point to another, it's always the terminal point minus the initial point. So it's y minus x. So that's the boundary map of A, and that's thus the image of del 1. And this is just gonna be the free abelian group spanned by this y minus x. So that would be the free group spanned by y minus x, and that is Z2 mod Z. And every time you mod a free abelian group or a tuple of a free abelian group by itself or by one copy, we just reduce the dimension by 1. So that's just isomorphic to Z. And of course, in the femboyized version, H0, I'll call it F, H0 of X, that's just FZ. So geometric interpretation of here is that there's only one class of simplices that are in here. If there are two classes of simplices, like it goes round like a meridian, and then there's one that goes this way, of course it would be Z2. And we'll see that when we compute the homology group of a torus. So right off the bat, this is a fundamental fact you guys need to know. If our space is path connected, it's only one component, one path component, then it's immediate that its 0th homology group is Z, or the integers, or its coefficient group is precisely Z. Right? So here's a fundamental fact. I'm gonna erase these things so that it stops lagging up. Okay, goodbye. Okay. So fundamental fact. If X is our space and it is path connected, then it's immediate that its 0th homology group is Z. And if it is a femboy space, its associated femboyized homology group FH0 of X is precisely FZ. So the Gaussian femboys. Okay, so that's a fundamental fact about path connected spaces. If it's not path connected, then it should have a different zeroth homology group. Okay. Like for example, this will be a much more advanced thing, but we will find out that the homology group of 2 points, it's not path connected, recall, but it's 2 points. Recall that, we'll see that the first homology group, or the zeroth homology group, is precisely z, direct sum z. So it's not, so h0 of x is not isomorphic to z simply because the space is not path connected. And we'll show later why that's the case, or in a different lecture. All right, so let's bump the complexity up a bit and let's introduce some two simplices into our space. Okay, so this time I'm going to consider a triangle. I'm going to consider a triangle, a legit triangle, or maybe we can try to, let's start with maybe finding the homology of a 2-simplex. And then we'll move on to the circle. So let's consider a disk. What is the homology of a disk? So D2. So, or maybe FD2. So a prosciutto, perhaps, maybe we can let's try to find the homology groups of a prosciutto. Or a 2-meat, close 2-meat. So first of all, let's triangulate this and turn it into a simplex, a 2-simplex containing 3 vertices and 1 face. So these are homeomorphic, so I can do that. And then let's pick an orientation. I'm gonna go this way, this way, this way. So counterclockwise. And let's label the vertices X, Y, Z, A, B, C. All right. So right off the bat, you guys can see that we have 3 vertices. Excuse my English. 3 edges, 1 face. So I'll call the face A. And so you guys can notice we have a face, we have an area, we have a 2-simplex in there embedded inside this triangulation. So it's immediate that our chain complex comprises a C2, and then a C1, and then a C0, and a 0. Of course, we have our maps del3, del2, del1, del0. So here's a tip. You could compute of course, you gotta find the groups first, find the abelian groups first, and then find the boundary map. But you guys can immediately inspect, or you guys can immediately see what the boundary maps are. For a surface A and for a volume element, which is, the 3-simplex here, the boundary is simply the addition of all of the boundaries. So for the case of a 3-simplex, it's the addition of all the faces, while for a 2-simplex, it's the addition of all the edges. So you guys can find out right away that the boundary map takes A to A plus B plus C. All right. And you guys can see immediately that based on our orientation, we have 3 separate maps for our edges. So the edge A is sent to X minus Z based on the orientation. Del of B is Y minus X. Del of C is Z minus Y. All right, so we have 3 separate maps that, and also, okay, A is just 1 face. We only have 1 face right here. We only have 1 2-simplex that is inside here. So it's immediate that C2 is only generated by 1 element. So it's a free abelian group generated by only A. And then C1, all right, we have 3 edges. We have 3 1-simplices, so it's generated by A, B, and C. C0, same procedure with the edges. Vertex. We have 3 vertices, or 0 cells, or 0 simplices, which is X, Y, and Z. And then you guys can see this is isomorphic to Z. This is isomorphic to Z cubed. And then isomorphic to Z cubed as well. or you can think of it as the direct sum of z with itself 3 times. And the same thing here. Okay. So we already know the boundary maps. How about finding the kernel? All right, so this one requires a bit of thinking. So let's go, let's try to compute the first homology group. So first homology group. So actually, here's another fact though. If our space is contractible to a point, so notice how I can homotope this entire space onto a point. Right, I can contract it to a single point. There is a deformation retract that shrinks the entire thing into a point. Then it's immediate that its homology group is isomorphic to that. So homotopies. So if two spaces are homotopy equivalent via homeomorphism maybe or a deformation retract, then it's immediate that there is an isomorphism between their homology groups. So you can derive from that fact that the homology groups HK of F D2 is immediately isomorphic to HK of a point, a single femboy F. But we're gonna go through the full computation right now. All right, so H0 of X is again the kernel of del 0 mod the image of del 1. So the image of del 1 is spanned by three elements: x minus z, y minus x, z minus y. So I'm just gonna write it down as del A, B, and del C. Del A, del B, del C, and you guys can see it right above there. And the kernel of del 0, of course, is the entire group. So that is Z. Wait, this is a bit weird. Yeah, okay, that's the same thing. 1, 2, 3, 4. This is a bit weird. Okay, this is Z3. And one of these guys should go off to 0, I suppose. And then this is supposed to give me Z1 because of course it's a path connected space. So that would just become Z2, no, Z1. And then something here vanishes. So that's the zeroth homology group. Right. Okay. So the first homology group of X actually this detects how many holes there are in the one-dimensional sense. So there are no holes here. Notice how there are no holes. If I draw a path, no matter how wacky it is, and I try to homotope it to a point or to a constant map, it gives me, I'm able to do that basically at every point here, at every region of FD2. So it's immediate that there are no holes. So it would be some 0 multiple of the integers. So it would be Z0. So let's verify that. So kernel of del 1. So it's the kernel of del 1. What's sent to C0? It's in fact the entire space. And then what's the image of del 1? It's precisely 3. It's generated by 3 of these guys. Oh, wait. Sorry, this is del 2. I mean del 2. What's the image of del 2? Well, it's just 1 here. So it's generated by one element, AB plus C, or A plus B plus C. And no, the entire thing is not sent to. Okay, so here's the thing with kernels. We will have to do a special algebraic procedure where we consider all possible tuples or all possible linear combinations and then set it to 0. So the kernel of del 1, it's spanned by a linear combination such that the linear combination of those edges gives me 0. All right, so it's I'll call it L A plus L. Oh no, I'll call it m b plus n of c. It's set to 0. So these are the images of my a, b, and c, right? And so I want it such that it's 0. So this is L of, okay, what's a in this sense? It is x minus z plus m y minus x plus n times z minus y, and that's equal to 0. And then you can expand this out, lx minus lz. This is, I know this is gonna be a boring part. You guys can skip it if you want. My minus mx plus nz minus ny equals 0. And then we can group together like stuff. So lx minus mx. And then we can group together nz minus lz, and then my, and then ny. And then we can separate out each of these guys, factor out each x, l minus m times x plus n minus l times z plus m minus n times y. And you guys will notice that it will be the case wherein this entire thing would equal 0 only when L equals M equals N equals 0. So L equals M equals N equals 0. That's only the case when it's like that. Or it's just M equals N. L equals M equals N. So we end up with a group spanned by X plus Y plus Z. So that is over here. Not Z, but actually, yeah, it is isomorphic to Z. So it's XYZ mod A plus B plus C. And then that's isomorphic to Z mod Z. And that gives us the trivial group. So we collapse every point in Z onto a single point. And so that's just 0. That's just the trivial group. So about H2. Now really there are no two-dimensional holes here as well. So the higher homology groups just vanish. All right. So as I said, we only have 2 dimensions here, and from this fact I said a while ago, when K goes beyond the dimension of X, its homology groups immediately vanish. So we can say that HK of our FD2, so I'm just gonna femboyize it here. So usually homology groups are defined piecewise because we have multiple values for K and we have to consider multiple stuff for K. So it is FZ for K equals 0 because it's path connected, and it is 0 for K greater than 0. And this is actually true for every contractible space. If I consider a covered or a ball, this is a sphere, but if I consider the volume inside of it a ball, it's contractible to a point, so it would have the same homology group as FD2 over here. Okay, so now let's go move on to the sphere. So this one is different in the sense where it has a 2-dimensional hole inside of it. No, it's, yeah, 2-dimensional hole. So a circle, 1 vertex X, 1 edge A. All right, so this one's actually pretty trivial. So it's just 0, Z, Z, and then 0. This actually gives me a split complex and a split exact sequence. So I didn't define a while ago what makes a sequence exact. So I'm saying that a sequence is exact. So in general, this can be any object, not just abelian groups anymore. So if I have, you know, and then C, can't draw C, okay, Cn minus 1, Cn minus 2, and then, you know, so on and so forth. And then I have maps, del n minus 1, del n plus 1 del n plus 2. Okay, so if I have these maps, I'm saying that this sequence of objects with these maps is exact when, the one is that composing two consecutive maps gives me 0. And I can compute a homology from these guys. So this is when the kernel of del n minus 1 is contained inside the image of del n. And this fact here allows us to compute homology groups because, of course, if I'm going to compute a quotient group, the normal group I'm quotienting by, or the subgroup or the group I'm quotienting my usual group or my given group by needs to be inside the group. And in fact, it needs to be a normal subgroup, right? So, but we're not strictly enforcing that the kernel of del minus 1 needs to be a normal subgroup of the image of del n. Okay, so that's exact. So a split exact sequence is another example of an exact sequence wherein if I consider only 3, so disregard this for now. If I consider 3 of these objects, the direct sum of this group and this group is precisely this group. And that's true. Z direct sum 0 gives me, of course, a different group of integers z paired with 0, such that z, of course, is inside the integers. But I can pair each of these, pairs with a z, an integer z, which is like a projection of some sorts. And so it's just isomorphic to z. So z direct sum 0 is isomorphic to z. And so that satisfies my thing for a split exact sequence. So if I have 3 objects A, B, C, and then they're in a sequence, it's a split exact sequence when, of course, it's exact, and when I have an object hemmed between 2 objects, those 2 objects comprise this object in the middle. That's a split exact sequence. Okay. So we have one edge and one vertex. So it's generated by A, it's generated by X, and really we can only compute the first and the zeroth homologies. So the zeroth homology of X, or S1, so S1, is the kernel of del 0 mod image of del 1. So the kernel, everything that's sent to, elements are sent to 0 is the entire Z mod. Okay, so what's the image of del 1? That's really just trivial, a trivial group. All right. So this is just Z. And it's true because S1 is path connected. If I choose 2 points, say over here and here, I can build a path between them. So just trace along the circle. So what about this kind of path here? Well, that doesn't matter because, of course, there's a hole there. All right. So next, let's compute the first homology group. So this one, it's not trivial this time because we have a 2-dimensional hole there. Or at least a 1-dimensional hole. It's a bit hard to define what holes are, but yeah, it's the dimension of a given homology group. So for kth homology group, that's the dimension of the hole inside X, or of a given hole. If there are no 2-dimensional holes in there, then the dimension of my second homology group must be 0. Or, yeah. Okay, so, all right, so this is the kernel of del 1 mod image of del 2. The image of del 2 is immediately 0. And so the kernel, whatever is sent to 0 in del 1, that's just the entire thing, C. So that's just Z. And of course, the higher homology groups just vanish. So HK of S1 is this piecewise function. It is Z for K equals 1 and 0, and 0 for K greater than 1. All right. And of course, my Femboyized version. So FS1, so it's a thigh and n-thigh of FS1 is the same thing, but Femboyized, of course. Fz for k equals 1, 0, and 0 for k equals 1. All right. So those are some sample computations homology. And you guys can see how this is much, much easier. We don't need to use theorems right now. There will be theorems like the excision theorem, the Mayer-Viatori sequence, but we'll get to those in a future lecture. So that'll be it for this introduction to homology with femboy spaces.